Welcome to Study Loop.
We're told that in a physics lab experiment, one end of a horizontal spring that obeys Hooke's law, so the force is linear proportional to the displacement or to the change in length, is attached to a wall. The spring is compressed 0.4 meters, and a block with mass 0.3 kilograms is attached to it. The spring is then released, and the block moves along a horizontal surface. Sensors measure the speed of the block after it has traveled a distance d from its position. Um, the measure values are listed. The data shows that the speed v of the block increases, then decreases as the spring returns to its unstretched length. Explain why this happens in terms of work done on the block by forces that act on it. Okay, well, to start off here, so as the spring decompresses, it does work on the block. Once the block passes the point where the spring is neither compressed or stretched, the block will start doing work on the spring. But friction will always be taking energy from the block, acting to slow it down. So what we have here is if there was no friction, then we would actually reach a peak speed at 0.4. Okay, so it would go like this. Instead, we have something that goes like this. And why that is because of the friction. The friction is slowing it down, is taking a lot of energy from the system. And in fact, it looks like even if we continued on with taking data, that it would actually stop when it got to 0.4, which is at the equilibrium. So you basically, what you did is you compressed the spring, and then the block just started moving fairly fast, and then started slowing down, and basically was going to just come to rest right about at the unstretched length of the spring. Because if there was no velocity at that point, which it looks like there was very little, um, there's no energy to then transfer back from the block into the spring to then stretch it. So it's basically just going to come to rest at the point where the spring is at its unstretched length. So then we're asked, let's see here, to use the work energy theorem to derive an expression for v squared in terms of d. Okay, so we have the potential energy in the spring. Okay, d naught is going to be our unstretched length, which is 0.4 meters, and then we have the rate of work done on the system by the friction force. Okay, so this is the power that's being dissipated by the friction force. So then we know that the kinetic energy of the block, and so then we have that the power, the rate of energy, the change in time rate of change of energy must equal the power flow out of the power into or out of the system. We can integrate this because F is a constant, and then V just becomes D. So we get that E is some constant initial energy, so the initial energy of the spring and the block, times this should be a D, times the work dissipated by the friction force, and then that equals so there's no initial kinetic energy in the spring or in the block, and the spring has a initial kinetic energy 1/2 k d naught squared. The energy at any given time then is 1/2 k times the change in length of the spring squared, so the energy stored in the spring at some given time, and then the potential energy in the block. So we can then solve for v squared. Okay, so we divide through by m, multiply through by 2, and we get this expression here where k over m times the quantity d naught squared minus d squared minus d naught squared, all that, and minus 2 times the friction force divided by m times d. Now, you can obviously simplify that a little bit, and we get it down to a form that looks like, so there's a d multiplying the whole thing, and then in here we have this expression here that also depends on d and d naught and the friction and the mass and the spring constant. So we were asked to then plot the data as v squared as a function of d. So I did that here, and so here are the data points, and then I just have lines connecting them. Okay, so this is v squared versus d, and then I took this function here, substituted in the value for d squared, or d naught, well this is 2d naught, and then had the computer fit this function to this data, doing I think a least squares fit, and we find that then, and basically saying that okay, d is our variable, and then k over m and ff over m are unknown fitting quantities, fitting parameters. And what we get from that fit is that k over m is about 40, and ff over m is about 7.83. If we then plug these back into here, then we get v squared as a function of d, and then we can plot that, and you can see this parabola here that actually fits the data very well. Then we can maximize that, and we find that v squared max is 1.67, which means that v max is 1.29 meters per second, and then that occurs at 0.204 meters, so right a little bit after here. Okay, so then we're asked to figure out what the spring constant is and what the coefficient of friction is. So we can do that. First, if we know the mass of the block, then k is 40 meters per second squared times the mass of the block, and that gives us 12.0 newtons per meter. So that is the spring constant. And then if we look at our friction, we can write our friction force as the kinetic friction coefficient times the normal force from the table on the block, which is mg. So the m cancels out, and we get mu k times g equals the value from our fit, 7.83, and so we get mu k is about 0.80.